So to start this look at integration, we're going to just have a look at some strategies, how to approach some integration problems. So, well, it might sound obvious, but the first thing you do is look for an obvious solution. So try to find some function, u equals g of x in the integrand whose derivative. In other words, it's that idea of derivative times function that, look for the obvious solution. So here's one. X on the square root of 1 minus x squared. Oh, hang on. We know the derivative of 1 minus x squared is minus 2x. So there's an obvious solution there. If I make the top minus 2x, then I've got derivative times 1 minus x squared to the power of a half, which is actually, and remember I was saying this the other day, du on root u, when you think about it, well, that's always 2 root u. Not on the reference sheet, but you'll be amazed how often that integral du on root u appears. So it's 2 times, well 2 times a half is 1, and root u, so minus root 1 minus x squared. So I'm sort of doing substitution without actually doing the substitution. In my head I'm saying I'll use this. Manipulate it to get it into a standard form. And that, I guess, again, is the whole idea of substitution. You want to try and get it in there. But sometimes you have to manipulate. So the standard integrals, as I said there, the whole reason we have them is to save time when integrating. So if I see something like this, integral of e to the x plus e to the x, so the power is x plus e to the x. I want to manipulate this so I get it into a standard form. So I remember my index laws, and you'll recall that we add the powers when we're multiplying. So I get e to the x times e to the x, and then I have it in the form derivative times function, because the power, you'll notice, is e to the x, and the derivative of e to the x is e to the x. So I have it in that form. Therefore, e to the x plus a constant. Second example, so there it is, 2e to the x on 2, 3e to the x plus 6. That is an inverse tan one, if you look at it real closely. Okay? Because e to the x is e to the x on 2 squared. And so the derivative of e to the x on 2, we can, again, manipulate this. We'll end up with that. 4/3 of a half e to the x on 2, which is the derivative of e to the x on 2, and I now have it in that inverse tan form. So we get 4/3 times 1 on a in this case is the square root of 2, inverse tan of the function e to the x on 2 over a root 2. And, well, we can tidy that 4/3 one up. So there we go. 2 root 2 on 3, inverse tan e to the x on 2 over root 2 plus a constant. Simplify the integrand if possible. So algebraic manipulation or trig identities, those sorts of things we might use. So, tan theta on sec squared theta. Shame it wasn't the other way round, because of course sec squared is the derivative of tan and we would have had derivative on function. But we got function on derivative, so something else is happening here. So what can I do? Well, I'll turn everything into sines and coses. And look what happens. We get sine theta on cos theta times cos squared on 1. And so now it's just sine theta cos theta. Oh, that's a half the integral of sine 2 theta. So by using my trig identities, I can actually turn that into quite a simple little integral. And sine, of course, goes to minus cosine. X cubed root 4 minus x squared. See again, derivative of x squared is 2x. I got x cubed. Derivative of x cubed is 3x squared, but the x squared's inside the square root sign. This is where I'm going to have to use some clever algebraic manipulation. So factorise by using the expression in the grouping symbol. So it's 4 minus x squared. That's the key to it. Bingo. I'm going to rewrite x cubed in terms of 4 minus x squared. And x cubed would be, well, minus x times 4 minus x squared would get me the x cubed. But I've got some bits left over. So the minus 4x, to balance it out, I need plus 4x. You think, what on earth? Why would you do that? Because now I can split it up into two things. One of them is minus x times 4 minus x squared to the 3 on 2. The second one is 4x times 4 minus x squared to the half. But now each of those is derivative times function to the power, because the derivative of x squared is 2x, and I've got that out the front. So I can add 1 to the power over the power, because it is derivative times function. Well, okay, I've got to balance it out. So this first one, I really wanted minus 2x, so I had to multiply by a half, and the second one, I would multiply by minus 2 to get the 2x. Isn't that beautiful? Oh, let's tidy that up. Ah, that's lovely. So algebraic manipulation can lead to some lovely integrals. Classify the integrand according to its form. So rational functions. If what you're integrating is a rational function, so polynomial division, partial fractions, which is a technique we'll look at in a few lessons, those sort of ideas I'd be looking for. Trig functions. Okay, if it's a trig function, have a look at the power of the trig function, and whatever that power is, that will probably determine what technique I'm going to use to go and integrate. Maybe it's a mixture of functions. I might have an exponential and a trig function, and they're the sort of ones we'd use the technique which we'll look at, integration by parts. But at the end of the day, there's pretty much only two methods to integration: substitution or by parts. So that's pretty much it. Because every other technique really is just using those ideas in some way. So all right, we'll just start off with 4a and 4b, see how we go with those.